All across the cosmos, and especially surrounding our own Milky Way galaxy, you can find these spectacular ancient collections of stars. We call them globular clusters. Imagine, if you will, a city of 1,000,000 stars, all packed together into a tight spherical ball. These stars are some of the oldest residents of the universe, having formed billions of years ago. They are like cosmic fossils, giving us a peek into what the universe was like in its infancy. For astronomers, these glittering spheres are more than just beautiful objects to look at. They hold fundamental clues about how galaxies, including our own, were built over cosmic time. They are truly magnificent. But for as long as we've known about them, globular clusters have presented a deep, nagging puzzle. The stars within a single cluster are remarkably uniform. They almost all have the same age and the same chemical composition, which suggests they were all born together in a single massive burst of star formation. The big question has always been, how? What kind of cosmic event could trigger such an intense and efficient creation of stars all at once, only to then completely shut down, leaving the cluster frozen in time? The conditions required to form these dense stellar cities have eluded a simple explanation for decades. Scientists have long debated the exact formation mechanism. One popular idea is that they form from gigantic clouds of gas. A rapid burst of star creation happens, and then the powerful explosions from the first massive stars to die, supernovae, blow all the remaining gas out of the system. This effectively stops any new stars from forming, leaving behind only the initial generation. However, this model doesn't perfectly explain the subtle chemical variations we sometimes see, or why these clusters are so different from other small galaxies. It's a good theory, but the details have been a source of ongoing scientific investigation and debate. This mystery is a perfect example of how much we still have to learn about the universe. We can see these objects, we can measure their light, and we can count their stars, but understanding their origin story is a whole other challenge. It's like finding an ancient city but having no records of who built it or why they left. To solve this puzzle, astronomers have turned to one of their most powerful tools, advanced computer simulations. These digital universes allow us to test our theories and explore possibilities that we can't observe directly, helping us to finally piece together the story of these stellar relics. To tackle the mystery of how star clusters form, scientists are now using incredibly powerful computer simulations. Imagine creating a digital copy of the universe inside a supercomputer. Researchers, like myself and my team, can input the fundamental laws of physics and watch as virtual galaxies and star systems evolve over 13.8 billion years of cosmic time. These simulations are so detailed that they can track the effects of individual supernova explosions across thousands of light years. By running these digital experiments, scientists can test different scenarios for star formation and see which ones produce objects that look like the globular clusters we observe in the real universe. These new simulations, known as EDGE, have revealed something completely unexpected and exciting. They predicted the existence of a whole new class of star system, one that bridges the gap between the familiar globular clusters and their larger cousins, dwarf galaxies. The researchers have named these objects globular cluster-like dwarfs, or GCDs for short. According to the models, these GCDs would look very much like a classic globular cluster, a compact bright ball of stars. However, their formation story and underlying structure would be fundamentally different, placing them in a category all their own, and potentially solving some long-standing cosmic puzzles. So what makes a GCD different? It all comes down to dark matter. A traditional globular cluster is thought to be a pure collection of stars, gas, and dust with no significant dark matter holding it together. In contrast, dwarf galaxies are much larger, more spread out, and are known to be embedded in massive halos of this invisible dark matter. The simulations show that GCDs are the in-between case. They are compact and dense like a globular cluster, but they form inside their own small, private halo of dark matter. This dark matter halo is the key ingredient that changes their entire life story. This dark matter halo allows a GCD to hold onto its gas a little bit longer than a normal globular cluster would. Instead of one single instantaneous burst of star formation, a GCD can have a slightly more extended, though still very intense, period of creation. This results in stars with a small but measurable spread in their ages and chemical compositions. This makes GCDs distinct from the uniform stars in a globular cluster, but not as varied as the stars in a dwarf galaxy, which can form stars for billions of years. This new category could be the missing link we've been looking for in galactic evolution. To find evidence for these newly predicted GCDs, astronomers didn't have to look far. Orbiting our own Milky Way, about 100,000 light-years away, is a tiny, faint satellite galaxy called Reticulum 2. For years, it was classified as an ultra-faint dwarf galaxy, one of the smallest and dimmest galaxies known. But its properties have always been a bit strange, making it a perfect candidate for one of these new GCDs. It is very compact, much like a globular cluster, but it also appears to be embedded within a halo of dark matter, which is a key trait of a dwarf galaxy. This combination of features makes Reticulum 2 a prime suspect. What makes Reticulum 2 particularly compelling is its star formation history. Observations even before this new theory showed that most of its stars were born in a very short, intense burst early in the universe's history. After that initial frenzy of creation, star formation seems to have shut down completely. This is very different from a typical dwarf galaxy, which would continue forming stars slowly over a much longer period. This one-and-done history is exactly what the computer simulations predict for a GCD, where a powerful event clears out the gas and halts further star birth, but not before a small, dark matter halo has shaped its initial evolution. Even more fascinating is the unique chemical signature of Reticulum 2's stars. They are extraordinarily rich in heavy elements created by a process called the R process, which is thought to occur during incredibly energetic events like the merger of two neutron stars. The fact that all the stars in this tiny galaxy share this same chemical enrichment suggests that a single, powerful event occurred very early in its history. This event seeded the gas cloud with heavy elements right before the main starburst happened, and then the system shut down. This story aligns perfectly with the formation model of a GCD. The case of Reticulum 2 highlights how new theories can make us look at familiar objects in a completely new light. What was once just a peculiar dwarf galaxy might actually be the first example of an entirely new class of cosmic object. It serves as a test case for the GCD hypothesis. If astronomers can confirm that Reticulum 2's properties match the predictions from the simulations, it would not only reclassify this one object, but would also strongly suggest that many more GCDs are out there, hiding in plain sight among the faint satellites of our galaxy and beyond. Confirming the existence of GCDs requires an observatory with extraordinary power and precision, and that's where the James Webb Space Telescope comes in. JWST is the ultimate tool for this job. Its massive mirror and highly sensitive infrared instruments can peer into faint and distant star systems with unmatched clarity. To prove an object like Reticulum 2 is a GCD, astronomers need to do two things. Confirm that it sits in a dark matter halo and precisely measure the ages and chemical makeup of its stars. JWST is uniquely capable of making both of these critical measurements, turning a theoretical idea into an observational reality. The telescope can map the motions of individual stars within a system like Reticulum 2. By tracking how fast the stars are moving, astronomers can calculate the total mass of the system. If the total mass is much greater than the mass of the stars we can see, that's a dead giveaway for the presence of a dark matter halo. This is the smoking gun that separates a GCD from a regular globular cluster. Furthermore, JWST's spectroscopic capabilities allow it to analyze the light from individual stars, revealing their chemical composition and helping to build a detailed timeline of when they formed. The search for GCDs is also a search for the very first stars that ever existed. The simulations suggest that some of these GCDs may have formed so early in the universe that they could still contain population 3 stars. The first generation of stars, made from only the pure hydrogen and helium created in the Big Bang. These stars have been a holy grail for astronomers for decades. Because GCDs shut down star formation so early, they might act as pristine time capsules, preserving these ancient stars for us to find. Finding even one population 3 star would revolutionize our understanding of the early universe. Ultimately, the discovery of GCDs would reshape our understanding of how galaxies form and evolve. It would show us that the dividing line between star clusters and galaxies is not as clear-cut as we once thought. Instead, there may be a continuous spectrum of objects, with GCDs filling a crucial gap in our knowledge. This quest, powered by advanced simulations and the unparalleled vision of the James Webb Space Telescope, is a perfect example of modern science in action. We are pushing the boundaries of what we know, searching for the missing pieces of the cosmic puzzle and, in the process, getting closer to understanding our own place in the universe.